timing is already mentioned. So it's always 9 to 11 only. It is fixed. Your schedule is fixed as 9 to 11 only. So why you are waiting? Okay, no issue. From now onward, always remember that the timings are from 9 to 11. Okay. So let's have a discussion on to the today's class, that is lecture number 5. Till now, we have completed a very important portion of combinational circuit, and we have learned how to design combinational circuit, how to design comparator, what are 1-bit comparator, 2-bit comparator, how to write the logical expressions of the comparator, how to identify the unequal number of combinations or equal number of combinations. We have also seen about the half adder, full adder, half subtractor, as well as single circuit for a half adder and half subtractor. Can you please let me know how many of you able to recall the entire yesterday class? So great. Everyone, please let me know by writing in the comment section, beta, that audio and video, everything is going perfect. If I am looking little bit down, it means I am looking to your comment section. Is it okay? If I am looking little bit down, this is the angle in which I can see your comment section. Is it okay? Great. So in today's class, first we will discuss in very short about the binary representation, and then we will move towards ones and twos complement, majorly twos complement. Yesterday also we have discussed that whenever we have to do the subtraction, we always do addition, but we take 2's complement of a number. 2's complement of a number will represent number itself but with a negative sign. Is it okay? Great, sir. Next we will move towards the concept of overflow, because we are going to discuss about the adders. So definitely if something is added, there is a possibility that the number of bits are not sufficient to represent the result. So that we are going to discuss serial adder and parallel adder. At the last we will move towards look ahead carry adder or carry look ahead adder. How many of you are ready now? Please let me know by writing in the comment section, beta ji. How many of you are ready now? Great. Mention in the comment section. Yes, sir, we are ready. Just mention in the comment section. I just wanted to see all of you in the comments. Hello, beta ji. Great. So all of you are ready now? Now let's have a small discussion on the number representation. We have already seen how to represent the binary number of any decimal equivalent. It is very easy by going with a simple format of 1, 2, 4, 8, 16, 32 combination. Is it okay? Now please observe, if we talk about representation of a binary number, then binary number representation can be done in an unsigned number or a signed representation. In an unsigned number, the magnitudes are only represented. So we say the number is a positive number. But if we have to represent separately about the positive and a negative number, then we will opt a signed magnitude representation. Now signed representation can be a magnitude, signed magnitude form where we have to represent a sign, and mantissa. Okay. Then we have one's complement form and we have two's complement form. Out of them, two's complement form is the most accurate form because it can deal with the arithmetic operation of positive, negative, 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 positive, every kind of a number. Is that okay? The same can be done by one's complement form as well, but in a one's complement form, we have 2 zeros, and this is the biggest demerit of having 2 zeros. Is it okay? So it is quite difficult to go with the one's complement with a negative number. It is easier to go with the two's complement. So we always prefer to go with the two's complement because in two's complement, arithmetic operation can easily be performed. How many of you now able to understand, beta ji? Great. Now please observe first unsigned number. What are unsigned numbers? See, I need your responses, beta ji. I need your responses because your responses are the fuel of my energy. Your responses actually are the fuel of my energy. Is it okay? Great. So Now please observe first unsigned numbers. If we talk about unsigned numbers, these numbers don't have any sign. By default, they are considered as a positive numbers because it is only representing the magnitudes. Is it okay? These contains only magnitude of a number. They contain only magnitude of a number. So representation of unsigned numbers are all positive numbers only. For a moment, suppose if we have to write the binary of 5 in 4-bit. How to write binary of 5 in 4-bit? We all know, sir, in 4-bit we have to represent 0, 1, 0, 1. All of you remember the 1, 2, 4 technique. This 1, 2, 4 technique is basically 2 to the power 0, position value, 2 to the power 1, 2 to the power 2, 2 to the power 3. Base is 2. And in the so on, it goes so on, 2 to the power 4, 2 to the power 5, if you are going to increase the number of bits. Is it okay? So basically, whenever we have to represent any decimal equivalent binary, then it is very easy. We can observe this is a coefficient which is going to multiplied with 2 to the power 1, which is nothing going to be 1 only. 2 to the power 1, 2, 2 to the power 2, 4, 2 to the power 3, 8, 16, 32 and so on. So if we want to write 5, it is very easy. The coefficient is multiplied with this. So 4 plus 1, 5. So 5. Is it okay? In the same way, if I am representing 1, 0, 1, 1. So it is the binary equivalent of which number? Can you tell me? It is the binary equivalent of which number? Sir, it is the binary equivalent of 1, 2. 2 plus 1, 3. 3 plus 8. 8 plus 3? Sir, 11. How many of you are able to understand, beta ji? So this number is representing 11. This binary representation of 11. Only representing the magnitude. In an unsigned number, only representing the magnitude. In the same way, if I am writing 7, then what is 7? 0, 1, 1, 1. Is it okay? Great, sir. Can you tell me what is the range of an unsigned number? If we talk about range of an unsigned number, then what is range of an unsigned number? Sir, range of unsigned number. If we talk about range of unsigned number, then what is the least number that you can represent? Sir, 0 for any number of bits. And what is the maximum that you can represent? Maximum decimal equivalent of the number represented. Sir, for a 4-bit, the maximum we can represent is the binary of 15. For a 4-bit, the maximum we can represent is the binary of 15. For a 3-bit, the maximum we can represent is the binary of 7. For a 2-bit, maximum we can represent is the binary of 3. Is it okay? Yes, sir. So can I say the range of unsigned number is from 0 to 2 to the power n minus 1. For 4-bit, we have 2 to the power n, 4, 2 to the power 4 minus 1 to the power 3. No, sir. 2 to the power n, that is 16, 2 to the power n whole minus 1. Can I write like this? Yes, sir. If we have a 3-bit, so 2 to the power 3, 8, 8 minus 1, 7. The largest number that you can represent is 7 and the least number that you can represent is 0. So 0 to 7 for a 3-bit, 0 to 15 for a 4-bit, 0 to 3 for a 2-bit. Is it okay? Yes, sir. So for a n-bit, we have the range of unsigned number, we have from 2 to the power 0 to 2 to the power n whole minus 1. 0 to 2 to the power n whole minus 1. How many of you now able to understand how to write any unsigned number? It is very easy to represent a binary representation of an unsigned number. Is it okay? It will represent number directly. All of you are able to understand. Please let me know by writing in the comment section, beta ji. Great. Now please observe. Let's have a discussion to sign magnitude representation. If we talk about sign magnitude representation, in this 1 bit, the most significant bit is used to represent sign bit and rest of the bits are representing magnitude. Is it okay? Now please observe, in sign magnitude representation form, the most significant bit represent sign. That sign is positive for 0 and negative for 1. If the most significant bit is 1, it is representing negative number. If the most significant bit is 0, it is representing a positive number. And the remaining represents the magnitude of the number. For a moment, suppose if we want to represent plus of 5 in a 4-bit. So let's have a 4-bit signed magnitude representation. Sign magnitude representation. If we talk about 4-bit sign magnitude representation, how to represent plus of 5? How to represent plus of 5? 0, 1, 0, 1. Basically, this 0 is representing a sign bit and this is representing a magnitude. So this is representing a sign bit. This is representing a sign bit, and 0 means 0 indicate positive, and this is representing a magnitude. How many of you able to understand beta ji? Please let me know by writing in the comment section. In the same way, if we have to represent minus of 5, then what is the way of representing minus 5 in a sign magnitude representation? In a sign magnitude representation, if we have, or say minus 4, suppose I am interested to represent minus 4, then how to represent minus 4? Please observe. Here this 1 is representing negative sign. This is a sign bit and a sign bit is negative. 1 means negative number. Is it okay? And we have a magnitude. Magnitude is 1, 0, 0. So how many of you able to understand the sign magnitude representation? In a sign magnitude representation, the most significant bit is indicating sign bit. If the most significant bit is positive, it represents positive number. If the most significant bit is negative, it represents negative number. Is it okay, beta ji? I need your responses, beta ji. If you are not going to type anything, how would I know that you are listening to the content? Huh? How many of you able to understand? Great. Need not to write everything. Just you can just put that 4-bit sign magnitude. Positive sign is represented by 0 MSB and negative sign is represented by negative sign is represented by 1 in the MSB. Can you tell me what is the range of sign magnitude representation? Can you tell me what is the range of sign magnitude representation? Can you tell me what is the range of sign magnitude representation? If we talk about n bit, what is the maximum number that you can represent? Sir, maximum positive number is plus of 7 and the minimum number is minus of 7. So from plus 7 to minus 7 we can represent. Plus 7 to minus 7 in a 4-bit we can represent. So it means for 4-bit we have 2 to the power n minus 1 negative number to plus of 2 to the power n minus 1 whole minus 1. So this is the basic range of sign magnitude representation. How many of you able to understand beta ji? Please let me know by writing in the comment section. How many of you able to understand the range of sign magnitude representation? Great. Same is for the ones complement as well. Now please observe. Next we have, how many of you able to understand beta ji? For a n-bit sign magnitude representation? Great. Because it can't deal with the arithmetic operation of a positive and a negative number within the range. So a new kind of representation is used called ones complement representation. Is it okay? Now let's talk about ones complement representation first. In a ones complement representation, even if you are present at that time, at the time of invention or at the time when all these things are created, you will do in the same way. If a number is positive, you can just take a reflection of the number, or you can say invert of all the units and say that that is a negative number. The same is used for the ones complement as well. Now please observe ones complement. In binary system, if each 0 is replaced by 1 and each 1 is replaced by 0, then the number is called ones complement of the given binary number. If we have a positive number, If we take 1's complement, we get negative number. If we have a negative number, if we take 1's complement, we get a positive number. Is it okay? Great, sir. MSB denotes the sign of the number. For a moment, suppose I want to write plus of 5 in 1's complement, in a 4-bit 1's complement format. In 4-bit 1's complement form. In a 4-bit 1's complement form, if we want to write plus of 5, so how to represent plus of 5? In the same way as we have represented plus 5 in a unsigned or plus 5 in a signed magnitude representation. But when we talk about to write minus 5, how to write minus 5? For writing minus 5, you have to invert each. Like if this is 1, so it becomes, it's 0, so become 1, 1 will become 0, 0 will become 1, 1 will become 0. So this is the representation of minus of 5. This is the representation of plus of 5. How many of you able to understand, beta ji? In the same way, if you want to write, say plus of 7. So what is plus of 7? 0, 1, 1, 1 in 1's complement. And what is minus of 7? Minus of 7 is 1, 0, 0, 0. This is minus of 7. Is it okay? Yes, sir. So what is the largest number you can represent? Sir, positive largest number in 4-bit we can represent is plus of 7. And if this is 0, the most significant, if it is 0, then it is a positive number in 1's complement form. If the most significant bit is 1, it represents negative number in the 1's complement form. Is it okay? Great, sir. Now please observe. Can you please tell me what is the range of 1's complement? What is the range of 1's complement? So, range of 1's complement number is also, for n bit we have minus 7, for a 3-bit is the, for a 4-bit is the least number, and plus 7 is the largest number. So smallest number minus 7, minus of 2 to the power n minus 1 whole minus 1, where n is 4, then you will get minus 7. Is it okay? 2 plus of 2 to the power n minus 1 minus 1. How many of you able to understand? For a 3-bit, minus 7 to plus 7. For a 4-bit, minus 15 to plus 15. And so on. How many of you able to understand the range of 1's complement number? The demerit of 1's complement number is, 2 zeros. Is it okay? And it will be difficult to deal with the 2 zeros in a negative number addition or subtraction. So it will become very difficult to go with the arithmetic operation of the negative numbers. Is it okay? How many of you able to understand, beta ji? Now please observe some disadvantages of 1's complement. Now please observe 2 zeros, plus 0 and minus 0. If you have to write plus 0 and minus 0. So plus 0 and minus 0 create logic and comparison issues. And around carry, add complexity to the addition. Whenever we are going to perform addition, we need to add 1 to the LSB. Then only the result will be correct. Okay. Insufficient for hardware. ALUs are harder to build. Arithmetical logical units with the 1's complement will become harder because we need to add 1 in the LSB once the arithmetic operation will be done. Limited range. The total range for a 4-bit is minus 7 to plus 7 only. Is it okay? So still the range is reduced by 1 bit. If you observe, the range is reduced by 1 bit. Rarely used because of the 2 zeros issue. Is it okay? So just remember that in 1's complement we have to deal with the 2 zeros, which makes the things complex. Now come to the 2's complement representation. This is the one which is accepted most for the arithmetical operation and mostly designed in all modern ALUs, arithmetical logic units. Is it okay? All of you are ready to understand 2's complement now? See, it's very easy and asked many times in GATE as well as PSUs. Please see, in 2's complement representation, if we talk about 2's complement representation, then how to calculate, how to find out 2's complement? If 1 is added to the LSBs of 1's complement, if 1 is added to the LSB of 1's complement, then we get 2's complement of a number. For a moment, suppose if we have a 4-bit 2's complement representation. If we talk about 4-bit 2's complement representation, so in a 4-bit 2's complement representation, how to represent plus of 7? How to represent plus of 7? Very easy, sir. 0, 1, 1, 1. We can represent plus of 7. Is it okay? Yes, sir. And how to represent minus of 7? To find minus of 7, first of all, we have to take 1's complement. First of all, we have to take 1's complement. So if you take 1's complement, it will become 1, 0, 0, 0. Then add 1 to the LSB. Then add 1 to the LSB. When you add 1 to the LSB, then it will become 2's complement of a number. Is it okay? So add 1 to the LSB. When you add 1, this 1 and 1, we have this number as a 1's complement. So 0 plus 1, 0 plus 1, 1, 0, 0, 1. So this is basically minus of 7. This is basically minus of 7. So in 2's complement, number will remain itself, but with a negative sign. In 2's complement, we can represent plus 7 as 0, 1, 1, 1, and minus 7 can be represented as 1, 0, 0, 1. How many of you are able to understand? Great. But it will be difficult to go with this. Let me make it easy. Please observe here. Please observe here how to represent any 2's complement number. Please observe here how to represent any 2's complement number. Suppose, please observe here, beta ji. I need your concentration. Please observe here. In 2's complement, most significant bit will be treated as a negative. Okay. Rest everything will be treated same as in case of binary. So we all know that this is your 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Is it okay? Yes, sir. Now please observe here. In this case, the most significant bit will be negative for 2's complement. In 2's complement representation, the most significant bit is negative. Is it okay? So we have basically, sir, 1, 2, 4, 8. And this instead of 8, we are getting minus 8 for 4-bit. In the same way, if we have 5-bit, then that will become minus 16. And rest of all are positive. Is it okay? So if I want to write a binary of, say, if I want to write a binary of 0, can we write binary of 0? Yes, sir. 0, 0, 0, 0 is the binary of 0. 2's complement as well as in unsigned magnitude. In all, we have 0, 0, 0 as it is. Now, if we talk about logic, if we talk about 1, how to write 1 in 2's complement? How to write 1 in 2's complement? Please observe, beta ji. 1 will become 0, 0, 0, 1. This is your 1 in 2's complement. Can you write 2? Yes, sir. 0, 0, 1, 0. Can you write 3? Yes, sir. 0, 0, 1, 1. So positive numbers are in the same way. In the same way, we can write for 4, 5, 6, and 7. In the same way, we can write for 4, 5, 6, and 7. So positive number in 2's complement will be represented in the same way as we have studied so far. Is it okay? Yes, sir. Now let's talk about, can you represent minus of 6? How to represent minus of 6? Or how to represent minus of 8? How to represent minus of 8? Can you represent minus of 8? Sir, this will be 1. If this coefficient is 1, we get minus 8 plus 0 plus 0 plus 0. So we will get minus 8. Can you write minus of 7, beta ji? Yes, sir. What is minus of 7? Most significant bit, if I make 1, it will become minus 8. Minus 8 plus 1, minus 8 plus 1 will become minus 7 in 2's complement. How many of you can now see minus 6 in 2's complement, beta ji? Very easy, sir. Minus 8 plus 2. Minus 8 plus 2 is minus 6 in 2's complement. How to write minus 5? Minus 5, very easy, sir. Minus 8. This is minus 8. How many of you now are able to understand? Plus 3. Minus 8 plus 3. Minus 8 plus 3 is minus 8 plus 3. How to write minus 4? minus 8 plus 4. How to write minus 3? Minus 8 plus 5. Minus 8 plus 5 is your minus of 3. In the same way, you can write minus 2 and minus 1 as well. How many of you now able to understand? Please let me know by writing in the comment section. If I ask you, find the signed number, find 2's complement signed number shown below. Can you tell me, beta ji, what is this number? 101101. Can you tell me what is this number in 2's complement? What is this number in 2's complement? Can you please tell me what is this number in 2's complement? Can you tell me what is this number in 2's complement? Sir, in 2's complement, can we write it as minus 16? Can we write it as minus 10? Can we write it as minus 12? Please let me know by writing in the comment section, beta ji. Sir, we have to observe from here. It is very easy to solve. First, observe this. So this will be your logic. This will be your 2 to the power 0. That is 1, 2, 4, 8, 16, 32. So how many of you can see minus of 32 because it's a 2's complement? So most significant is negative. Minus of 32 plus of 8. Minus of 32 plus of 8 plus of 4 plus of 1. So 8, 4, 12 plus 1, 13. Minus 32 plus 13. How many of you can answer now? Please let me know by writing in the comment section, beta ji. How many of you able to answer now? So this will be your minus of 19. How many of you able to understand, beta ji? Please let me know by writing in the comment section. See, minus 32 plus 13. Okay. Minus 32 plus 13. How many of you able to understand? Good evening, beta ji. Can you now observe any number? Okay. Can you tell me what is this number? You have to find which of the following is correct. Now please observe, beta ji. Option number A is 2's one 0 0 1 in 2's complement representation is minus 7. Okay. You have to tell me which of the following is correct. Can you answer which of the following is correct? Which of the following is correct? You need to answer which of the following is correct. You need to answer which of the following is correct. Can you answer, beta ji? Which of the following is correct? Can you answer which of the following is correct? Haji, beta. Please observe this question very carefully. Okay. And this representation is important to understand. Please see. Which of the following is correct? You have to identify. In 2's complement, representation is of minus 7 is of minus 7, which among the following? So if you observe the first one, this is absolutely correct. We all can see this is minus 8, 4, 2, 1. So minus 8 plus 1 minus 7. This is correct. Now let's talk about this 1, 2, 3, 4, 5. 5 bits. So minus 16, 8, 4, 2, 1. So what this will become? minus 16 plus 8. Minus 16 plus 8 is minus 8 only, and minus 8 plus 1 is a 7, minus 7 only. This is also correct. If we talk about this, then what happened? Sir, this will be your 1, 2, 4, 8, 16, 32, negative. Minus 32 plus 16. 16? Minus 16, minus 16 plus 8. Minus 8, minus 8 plus 1, 7 only. This is also correct. How many of you able to understand? It doesn't matter. If the most significant bit is high, then out after that, if n number of bits are going to be high only, then in 2's complement, it is representing a negative number only. You can just observe these three. Suppose if I have a number 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, and I ask you, what is this number in 2's complement? So you need not to start from here. Instead of starting from here, you can just observe this. Whatever this number, where this will be treated as a negative. Is it okay? The same you will get. It doesn't matter how many times you are increasing 1 ahead, because that is a negative only. So how many of you able to understand that all the 4 are correct? Betaji, please let me know by writing in the comment section. All are correct. So now we have information of 2's complement number. Now you can directly write the 2's complement. You can directly identify what is represented in 2's complement signed magnitude representation or an unsigned magnitude representation. Now you know about decimal to binary and binary to decimal, positive number as well as negative number. The thing is, why we want this 2's complement number? Now let's talk about arithmetical operation of 2's complement number in order to understand the concept of overflow. Please observe, Betaji. Suppose I am interested to understand the concept of overflow. This is very important for this year. So please observe very carefully concept of overflow. So how to understand the, what do you understand by the term overflow? Suppose if you have a cup and the cup is of 200 ml and you want to fit 250 ml, what happened? Sir, 50 ml get overflowed. Great. So it means you can't occupy more than the space allotted. In the same way, in binary number system or in our calculator system, the maximum that we can represent is the limit. If the number representation goes beyond that limit, we say overflow occurred. Let us first understand in terms of 4-bit. Okay. So consider 4-bit 2's complement arithmetic operation. Okay. Or consider 4-bit 2's complement addition. Okay. Yes, sir. Now please observe, Betaji. Suppose if we have plus of 4 and we have plus of 2, can we add plus of 4 and plus of 2? We have to represent in 4-bit only. So 4-bit plus of 4 means 0, 1, 0, 0. If we add plus of 2, 0, 0, 1, 0. If we are going to add these two numbers, what happened? This will be 0, this will be 1, this will be 1. 1 plus 0 is 1, 0, 0 is 0. So in this number, in this addition, if you observe in this addition, we are getting plus 6. We are getting plus 6 and the result is also plus 6 only. So this result is correct. Yes, sir. Here no overflow occurred. No overflow occurred. No overflow occurred. Why you are saying that no overflow occurred, Betaji? No overflow occurred because, sir, no overflow occurred because, sir, there is no extra digit required to represent our answer. Is it okay? The answer can be represented in the addition of the result of the addition can be represented in 4-bit only. Is it okay? No extra bit is required. No overflow occurred. No extra bit is required. Just let me write it here. First, no extra bit is required. No extra bit is required. So we don't need any extra bit to represent the result. Let me show you once again. Suppose if we want to add plus of 7 and I want to add plus of 6. So what is plus of 7? Plus of 7 in 2's complement is 0, 1, 1, 1. And what is plus of 6? 0, 1, 1, 0. When we are going to add plus of 6 and plus of 7, then what happens, sir? This will become 1. This will become 1, 1, 0, carry over 1. Triple 1 means 1. We all have observed the full adder. Yes, sir. So for triple 1, we get 1, carry over 1, and we are getting 1. Is it okay? Yes, sir. What this number is in 2's complement? In 2's complement, the most significant bit when becomes negative, the number will become, sir, minus 8 plus 5. Minus 8 plus 5. So this number is basically minus 8 plus 5 minus of 3. This is representing a incorrect result. So can I say that 2's complement won't able to do the arithmetical operation of numbers? No, I can't say this. Why? Because the result is absolutely correct in case if there is one extra bit represented. Why this happened? What is the maximum number that we can represent in 2's complement? What is the maximum number that we can represent in 2's complement? Sir, maximum positive number is plus of 7 for a 4-bit. And the minimum number that we can represent is 8. So what is the range of 2's complement? If we talk about range of 2's complement number, what is the range of 2's complement number? Range of 2's complement number is from minus 2 to the power n minus 1 to plus 2 to the power n minus 1 whole minus 1. It means if we have a 3-bit, it will be from minus 8 to plus 7. Minus 8 to plus 7. And what result we are getting while having the addition of plus 6 and plus 7? Plus 6 and plus 7, we are getting plus 13. We can't represent plus 13 in 2's complement sign magnitude representation with 4-bit. We need 5-bit. Is it okay? Yes, sir. So why it happened? Because you have only 4 bits. In a 4-bit, the maximum number you can represent is plus of 7. And you want to represent plus of 13. You can't represent. Here the overflow occurred. And that is why we are getting wrong result. If this extra bit is used, with extra bit, what happened? With extra bit, what is your result, beta ji? 0, 1, 1, 0, 1. So we are getting plus of 13. The result is correct. So extra bit is required. Whenever extra bit is required, it indicates overflow occurred. Whenever extra bit is required, that is overflow, it means it goes away from the range, occurred. So whenever extra bit is required, overflow occurred. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. So whenever an overflow occurred, the bit is being increased by 1 bit in MSB. If the overflow does not occur, no extra bit is required. No extra bit is required. No overflow. If extra bit is required, overflow occurred. Means you have the total number of bit is being increased by 1 bit. The total number of bit is being increased by 1 bit. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. Please let me know by writing in the comment section. Great. Once again, please observe. Can we deal with a positive and a negative number? Suppose if we have a plus of 7 and minus of 3. So how to perform plus of 7 and minus of 3? Now please observe. We can only do the addition. Subtraction will done automatically. In 2's complement sign magnitude representation, 7 can be represented as 0, 1, 1, 1. And 3 can be represented, minus 3 can be represented as minus 8 plus 5. Minus 8 plus 5. So when you are going to perform addition, automatically subtraction will be done. Now please observe, I am going to add these. So 1 and 1 will become 0, carry over 1. 1, 1, 0, carry over 1. Triple 1, 1, carry over 1. Triple 1, 1, carry over 1. Is it okay? Double 1, 0, carry over 1. How many of you able to understand? We have to represent the result in 4-bit only, and in 4-bit what is the result, betaji? Plus of 4. So this is the correct result. Minus 7, plus 7 minus 3 plus of 4. Correct result. This bit is not required. Not required. When not required means no overflow. When extra bit is not required, it means no overflow. When extra bit is not required, it means no overflow occurred. How many of you able to understand? When extra bit is required, overflow occurred. When extra bit is not required, just writing here once again, extra bit is not required, so no overflow. Whenever extra bit is required, overflow occurred. Whenever extra bit is not required, overflow does not occur. How many of you now able to understand? Can you please let me know? Sir, big fan of machine classes. Now it's a time for digital as well. So please let me know by writing in the comment section, betaji. Great. We all know if one number is positive and one number is negative, it can't go beyond the limit. Is it okay? Yes, sir. Now let's talk about negative number. Suppose if we have minus 3 and minus 4. So what is minus 3? Minus 5, minus 8 plus 5. This is a minus 3 in 2's complement. What is minus 4 in 2's complement? Minus 8 plus 4. So how many of you able to understand 2's complement, minus 3 representation in 2's complement, minus 4 representation in 2's complement? When we are going to perform addition, this will become 1, 0, 1, 1, 0, carry over 1, triple 1, 1, carry over 1. So what is the result? Can you please observe here? This minus of what we are getting? Minus of, please observe here, what we are getting? Minus 8 plus 1, minus of 7, and that is the correct result. This unit is not required. So no extra bit is required. That is no overflow occurred. That is no overflow. It is within the range only, na? Within the range only. So we can say no overflow, no overflow. If you observe, if I write minus of 5 and minus of 4, what it become? Minus of 5 means we have minus 8 plus 3. Minus 8 plus 3 is minus of 5. Minus of 4 is minus 8 plus 4. Minus of 4. Minus of 4. Minus of 5. If we add these two, what happened? If we are going to add two same sign numbers, means both are negative, then what happened? 1, yes sir, 1 as it is, 1 as it is, 1, 1, 0, carry over 1. What we are getting? We are getting plus of 7, which is a wrong answer. Would this 2's complement is not able to perform arithmetic operation? No, it is. We can do the arithmetic operation with the 2's complement, but the issue is this extra bit is required. If we consider this bit as well, then what happened? Minus of 16 plus of 7. Minus of 16 plus of 7, that will become minus of 9. So with extra bit, the result is minus 9. With extra bit, minus 9, which is correct. Yes, sir. So extra bit is required. Extra bit is required. Whenever extra bit is required, it means overflow occurred. Overflow occurred. But in most of the book, instead of saying this to be overflow, they say underflow. What is the meaning of underflow? It means it goes the value below the maximum, below the least value that we can represent in a 4-bit. So sometimes this overflow is represented with the term underflow for a negative numbers. Is it okay? So we called it as underflow. The things are same. It is below the range. Above the range, below the range. Above the range, overflow. Below the range, underflow. How many of you now able to understand, betaji? Can you please let me know by writing in the comment section? Sir, now we know about the arithmetic operation of a binary number, positive number, negative number, 2's complement representation. Is it okay? Yes, sir. Now there is one very important part. Please observe here. when the overflow possibility, when the overflow can occur. If we observe two same sign numbers, if we observe two same sign numbers, please observe here, both are positive. If two same sign numbers are added, please observe, everyone, please observe here. If two same sign numbers are added, this is also positive, this is also positive. And in result, if the sign is same, no overflow occurred. No overflow occurred. When the same sign numbers are added, when the same sign numbers are added, -1, -1, hai na? This is -4 and -3, minus, minus. When the same sign numbers are added, and in result, if the sign is same, no overflow occurred. However, if two same sign numbers are added, if two same sign numbers are added, and in result, if the sign is opposite, we are adding positive numbers, we are getting negative. So when two same sign numbers are added, and in result, if the sign is opposite, when two same sign numbers are added, when two same sign numbers are added, -4, -5, when two same sign numbers are added, in result, if the sign is opposite, overflow occurs. So can I say, in 2's complement arithmetic operation, when two same sign numbers are added, and in result, if the sign is opposite, then it represent overflow occurred. Whenever overflow occurred, bit is being, you can say, result is being increased by 1 bit extra. The result is being increased by 1 bit additional. How many of you able to understand, betaji? Great. So let me write it, let me have this in the words. Please observe here, beta. First thing that we are observe is the range of 2's complement number is -2 to the power n minus 1 to +2 to the power n minus 1 whole minus 1. Is it okay? -8 to +7 for a 4 bit. Now please observe, if an arithmetic operation of n bit is performed in 2's complement, if an arithmetic operation of n bit is performed in 2's complement, then situation may arise is when it requires one more bit to show the result. When additional one more bit is required, then this condition is called overflow occurred. So whenever overflow occurred, the bit is being increased by 1 bit in MSB. Is it okay? Yes, sir. When two numbers of opposite signs are added, when two numbers of opposite sign, one is positive, one is negative, never overflow occur. Okay, so overflow does not occur. Whenever two opposite sign numbers are added, overflow do not occur. When two same sign numbers are added, then there is a chance of overflow. When two same sign numbers are added, then there is a chance of overflow. Is it okay? So I'm just writing, please observe. A note point. When two same sign numbers, are when two same sign numbers in 2's complement representation are added and in result, if the sign is opposite, then it indicates overflow. Then it indicates overflow. When two same sign numbers in 2's complement representation oh, just a minute, betaji, just a minute. Can you please tell me, Whether the screen is now visible to all of you? Can you please tell me, beta ji, whether the screen is now visible to all of you or not? Okay, great. I'm extremely sorry for this. Can you please tell me whether the screen is now visible to all of you or not? There is some fluctuation happened, and because of that, your camera get off. So, is it now okay? Now the screen is okay, beta ji? Now the screen is okay. Can you please tell me now the screen is okay? Can you please tell me now the screen is okay? Can you please tell me now the screen is okay? Can you please tell me, beta ji, now the screen is okay? Can you please tell me now the screen is okay? Can you please tell me now the screen is okay? Great. Because of the writing I did this, please do the correction here. Okay. So now it is visible to all of you. The screen is now visible to all of you. When two same sign numbers in 2's complement representation are added, and in result, if the sign is opposite, then it indicate overflow. Suppose in 2's complement representation we have two MSB A and B. Let A and B are the MSBs of 2's complement signed number. Let A and B are the MSBs of 2's complement signed number. 2's complement signed number. Let A and B are the MSBs of 2's complement signed number, and signed number. MSBs of 2's complement signed number, and C is the resultant MSB after adding two numbers then overflow condition will be. What is the overflow condition? Can you please tell me, beta ji? If A and B are the MSBs of two numbers, if A and B are the MSBs of two numbers, everything is running perfect, huh? Okay. So if we talk about 2's complement, so A and B are the MSBs of two numbers. Suppose if we have this A and B, so if we add A, B and we get C, if we add A, B and we get C, if we add A, B and we get C, if A is high, B is high and C is also high, no overflow. If A is low, B is low and C is also low, no overflow. Overflow condition occurred when two same sign numbers are added, and in result if the sign is opposite. So A and B are high, C is low, or A and B are low, C is high. So if any one of this is high, that indicates overflow occurred. So this is the overflow condition. How many of you able to understand, beta ji? How many of you able to understand? Please let me know by writing in the comment section, beta ji. How many of you able to understand up to this part? Now one more very important, please observe here. How to identify overflow. Whenever we are designing any serial adders, this is what we are going to perform. Group of bits we are going to add in the serial adder, in the parallel adder, in the look ahead carry adder. Is it okay? So where we have to add group of bits, there is a possibility of having overflow. So instead of showing the result, it must show error signal. And how to identify that error signal? That we can go with the arithmetic operation of 2's complement. If we are using the addition by using 2's complement, then we can show the error whenever it goes beyond the range. It is possible by observing the carry in to last bit position and carry out from last bit position. Please observe this addition. 0 0 will give 0, 0 1 will give 1, 1 0 will give 1. What is carry in here? What is carry in here? When you are performing the addition, what is carry in here? We have a carry in as a 0. Is it okay? 0 0 0 when we add, what is carry out here? What is carry out here? Carry out is also 0. So whenever carry in and carry out are same, in last bit position carry in and from last bit position carry out, whenever these two are same, no overflow occurs. Please observe once again. What is carry in here? What is carry in here? 1 1 0 we get 1, carry over 0, then 1 1 we get 0, carry over 1, triple 1 we get 1, carry over 1. So here we have carry over 1, and what is carry out? We are getting carry out as a 0. 1 0 0 when we add we get 1 or 0. So carry out is 0 and carry in is 1. Whenever the carry into the last bit position and carry out from the last bit position are different in 2's complement arithmetic operation, we get overflow. That means overflow occurred. Whenever carry in to last bit in 2's complement arithmetic operation and carry out from last bit of 2's complement arithmetic operation are different, overflow occurred. Great, sir. Please observe once again. If you observe here, what is carry in here? What is carry in here? And what is carry out here? So, sir, 1 0 1 0 0 0 1 0 1 1 0 carry in is 1 and carry out is also 1. Whenever carry in and carry out are same, no overflow occurred. Whenever carry in and carry out are same, no overflow occurred. If you observe here, what is carry in here? If you observe carry in here, 1 1 1, carry in is 0, however carry out is 1. So whenever carry in and carry out are different, overflow occurred. Is it okay? So in 2's complement arithmetic operation, if carry in and carry out from last bit position are different, overflow occurred. So in terms of carry in and carry out, can I conclude in 2's complement arithmetic operation, condition, overflow condition, overflow condition in 2's complement operation, in 2's complement operation, carry in and carry out can be represented as carry in and carry out. XOR operation, it will be better to write. So overflow condition in 2's complement, carry in and carry out. Whenever carry in and carry out are different, then we can say whenever they are different, we can say no overflow. So if the result is this, whenever the carry in and carry out are same, XOR gate, no overflow. Whenever carry in and carry out are same, no overflow. Whenever carry in and carry out are different, we all know about XOR gate. XOR gate output logic is 1 whenever the inputs are different. Then overflow occur. Overflow or underflow occurred. How many of you able to understand up to this part, beta ji? Please let me know by writing in the comment section. If there is any issue, please let me know by writing in the comment section, beta ji. So in 2's complement operations or in 2's complement mathematical additions, we can say carry in and carry out from last bit positions if differ, overflow occur if carry in and carry out to last bit position and from last bit position are same, no overflow occurs. So this is used for our arithmetical operation whenever we are going to perform a serial adder, parallel adder, or your look ahead carry adder. So how many of you able to understand, beta ji? Please let me know by writing in the comment section. Can you answer this one? I need your responses. I need your responses. Can you answer this one, beta ji? Can you answer this one? All of you able to understand about the 2's complement and overflow concept? All of you able to understand the overflow concept? Yes, sir. Now, can you tell me the addition of 4-bit 2's complement binary number 1101 result in? So, if you observe, this number is a positive number and this number is a negative number in 2's complement. MSB is 1, MSB is 0. So, if the two numbers are of different sign, no overflow. Overflow cannot be occurred. So these two can't be the answer. Is it okay? This kind of things are required for engineering services. You need not to go, you can directly mark your answer. However, if you observe, we have to find the result as well. What is this? This is minus of 8 plus of 5. Minus of 8 plus of 5 means minus 3. Minus of 8 plus of 5 means minus 3. What is this? Plus 4. Minus 3 plus 4. Minus 3 plus 4, definitely plus 1. So plus 1 means this is your answer. You need not to move your pen even. How many of you able to understand, beta ji? Great. So it's okay. If we are presented there, we can easily do the addition. But actually, our arithmetical logic unit has to perform the addition. Now let's try to understand what is there in the ALUs. How we can use the group adders in the ALUs to perform the arithmetical operations. Is it okay? It is visible now, beta ji? Great. Now please observe. First, let us talk about group adders. We are interested to add group of bits. So we have group adders to add group of bits. Suppose if I want to add 6 and 4. So 6 is 0, 1, 1, 0 and 4 is 0, 1, 0, 0. Here we have one number called A number. So I am representing A3, A2, A1, A0. Another number we have B number. So I am writing B1, B2, B3, B4. Let me represent once again. 0, 1, 0, 0. So this can be represented as B3, B2, B1 and B0. We want to perform the addition of these two numbers. So we are not interested to add either only A0, B0 or either only A0, B0 and C0. We are interested to add group of bits. And how you will do the addition? Sir, general approach is we will add these LSB bits. We will get them some bit and a carry bit. Then we add and we move ahead. Is it okay? How many of you able to understand? Yes. So whenever we have to add group of bit, we can use one of the digital circuit called group adders. Now the group adders are used to perform addition of group of bits. Is it okay? So to add group of bits, one of the following circuit can be used. First one is your serial adder. Second one is your parallel adder and third one is your look ahead carry adder, also called as carry look ahead adder. Both are the same thing. So carry look ahead adder. We have total 3 types of group adders. Let's first talk about serial adder. Please write down serial adder first. So if we talk about serial adder is the adder which is slowest among all. Serial adder is the slowest adder among all, but there is one advantage. The advantage is only one full adder is used to add any number of bits. Is it okay? But it is the slowest adder among all. It is more useful when we have the data coming from different registers. Is it okay? And we have to perform the addition as well. Only one full adder can perform n number of bit addition. Is it okay? Here we have to use 3 shift registers, in which one is called as PISO, two PISO and one SIPO. Is it okay? So total 3 registers are required. Registers are a sequential circuits where the data is being stored in different flip-flops. Is it okay? So I am going to explain the serial adder after we are going with the shift registers. Is it okay? Because then only you can able to understand it in a well way. So presently I am just mentioning those things which is required to be remembered, and when we are going with the registers, then I will explain the serial adder once again. Okay? Yes, sir. Please observe, beta ji. It is the slowest adder among all. There is only one full adder is used to add group of bits, and shift registers are used to shift the data one by one bit. Shift registers are used to shift the data one by one bit. How many of you able to understand? Please let me know by writing in the comment section, beta ji. Great. It requires n number of clock pulses to add n bit. It requires n number of clock pulses to add n bit. So if we have to perform 4 bit, it requires 4 clock pulses. If we have to perform addition of 10 bit to 10 bit numbers, it requires 10 clock pulses. Is it okay? You don't know about clock pulses, what is clock pulses, what is resistor, how a 1 by 1 bit shift operation will be done. Need not to worry, just mention up to this part. Rest we are going to understand in registers topic. Is it okay? Great, sir. So now I am moving towards the next adder. Because it is a slow adder, only one full adder is used to add n number of bits. This is a slow adder, only one full adder is used to add n number of bits. So we want to have a faster adder. The faster adder from this is a ripple carry adder. This ripple carry adder is also called as parallel adder. So please write down. Next one is your parallel adder. Let's try to understand parallel adder first. Parallel adder, it is a combinational circuit which performs addition of 2 binary numbers in parallel. So basically it is a combinational circuit which performs addition of two binary numbers in parallel. Is it okay? Yes, sir. It consists of full adders connected. It consists of full adders cascaded with the output carry of one full adder connected to the input carry of next full adder. So it consists of full adder connected in cascade with the output carry of one full adder connected to the input carry of next full adder. There is a propagation delay present in this type of errors. There is a propagation delay present in this type of adders. Let's try to understand with a basic 4-bit ripple carry adder. Is it okay? Yes, sir. Okay, if I ask you to design a adder, how would you design for a n-bit addition? Sir, if you ask me to design, please observe, then A3, A2, A1, A0 is one number, suppose, and we have B3, B2, B1, B0, another binary number. If we have to perform the addition, while doing this, first we perform the addition of A0, B0. This will give S0 and there will be the C1. Then we need to perform the addition of this. This will give S1 and we get C2. We need to perform this, we get S2 and C3. We need to perform this, we get S3 and C4. In this way, even if I will ask you to perform the addition, you are performing the addition the same way. Yes, sir. In previous, we have seen in 2's complement as well. We have done all the additions in the same fashion. Same is done with a ripple carry adder as well. So in a ripple carry adder, if we have to perform the addition, then addition will be done parallelly, and the connection is there is n number of full adders connected, cascaded with the output carry of one full adder connected to the input carry of next full adder. So basically, if we talk about 4-bit parallel adder, if we talk about 4-bit parallel adder, so how a 4-bit parallel adder performs its operation? Everyone please observe. Now the things are going in a very good one, in a very like useful for your gate exam form. Okay, so please observe here. We have one full adder. Let me show you one full adder. One full adder will have sir, input, 3 input, 1, 2, 3 input and 2 output. One is called as a sum, another one is called as a carry. Okay, yes sir. So we have a sum and a carry, and if we talk about carry out, and we have inputs we have A, B and C. Is it okay? Yes sir. So for a 4-bit, if we talk about 4-bit, we need 4 full adders. For a 4-bit, we can use 4 full adders. Cascaded, 4 full adders cascaded with the output carry of one full adder connected to the input carry of next full adder. Output carry of one full adder is connected to the input carry of next full adder. Output carry of one full adder is connected to the input carry of next full adder, and so on. That is why the name ripple carry adder given. We have the numbers. We have a number A. Number A is having A3, A2, A1, A0. So we have the data A3, A2, A1, A0. At the same time, we have the data B3, B2, B1, B0. So we will apply A3, B3, A2, B2, A1, B1, A0, B0. Initial carry in case if not given, you can consider 0. If given, let us suppose some intermediate addition get started. So we need that initial carry as well. Is it okay? Otherwise, generally, most of the cases we take initial carry 0. Now we have one full adder, another full adder, another full adder, another full adder. So I'm just making this as full adder, not full adder 1, full adder 2, full adder 3. Is it okay? So full adder not will give sum out as S0. This will give sum out at S1, S2 and S3. Your result, your addition will be performed when all the sum bit and carry bit are available. Is it okay? Yes sir. All of you are aware with the internal circuitry of the full adder? Yes sir, we remember about the internal circuitry of the full adder. All of you are remembered? Yes sir. If you remember the internal circuitry of a full adder will have A XOR B. One full adder will have A XOR B, AB, BC, CA passed through one OR gate. This is a full adder. If all of you have remember, this is a full adder. ABC, AB, AC, BC. This is a full adder. Yes sir. We all able to recall this full adder. This is basically a full adder. Hoping all of you able to recall the full adder. Yes sir. For a moment, suppose if each logic gate will have a delay of TPD, then what is the minimum time delay required for some bit to generate? Sir, 2 TPD time. One TPD will give you the output of this level, another TPD will give the output of this level. In the same way, since each logic gate will have a delay of TPD, then 2 TPD time is required to have carry out as well. Is it okay? Yes sir. Now please observe here. If each logic gate will have a delay of TPD and the full address will be designed with a 2 XOR gate, 3 AND gate, 1 OR gate, then after applying the inputs, we must have to wait for 2 TPD time for carry C1 to generate. It means We have A1, B1, we have A0, B0, we have A2, B2, we have A3, B3. But we can't directly do the addition of A3, B3 until unless we don't have C3. We can't do the addition of A1, B1 until unless we have C1. Otherwise, this will give wrong result. Is it okay? Yes, sir. If you will not add these two, instead of adding these two, if you directly add these two, then the result will be wrong. Yes, sir. Simple. It will take TPD 2 TPD time to generate carry C1. Once carry C1 generated, then only all the inputs are valid inputs available at the input of full adder 1. Now full adder 1 again takes 2 TPD time to generate carry C2. Now C2 gets generated in, from starting if we talk, the total time is 4 TPD. Because C1 comes here after 2 TPD time, when all the inputs are there, then further 2 level delays are there and carry out will be generated post 4 TPD delay. After 4 TPD delay, all the inputs are available, to the full adder 2. Now only it will perform correct addition, and its logic circuit will take another 2 propagation delay time to generate carry C3 and S2. So it will take 6 TPD time from initial to generate C3. Once C3 is available, then only you can say all the 3 inputs, valid inputs, are available to the full adder. Now this full adder again takes 2 TPD time to perform addition S3 as well as C4. So C4 and S3 both are available after 8 propagation delay time. How many of you able to understand, Betaji? Yes, this method is slow, faster than serial adder, but still it is slow. Why it is slow, sir? With the increase in number of bits, the time of addition changes. With the increase in number of bits, time of addition changes. Is it okay? The data applied also changes the time of addition. How many of you able to understand, Betaji? How many of you able to understand up to this part? Please let me know by writing in the comment section. How many of you able to understand up to this part? Please let me know by writing in the comment section. Okay, great. So now please observe, Betaji. Now please observe, Betaji. If we have a, can we reduce the time? Can we reduce the time? Can we reduce the time? Sir, if the fresh addition is going to perform, then C0 is not required. So instead of using a full adder, we can also use a half adder here. Yes, sir. So you can also use a half adder here and use 1, 2, 3 full adder. Then also A0, B0, S0, C1. C1 is the input. A1, B1, S1, C2. C2 is the input to this. We have A2, B2, S2, C3. C3 is the input to this. We have A3, B3, S3, C4. How many of you now able to understand, Betaji? Please let me know. In case if the only fresh addition need to be performed, then one half adder can perform this A0, B0. Of course, the time delay reduced to half if we are using only one half adder. This can also be done by using 2 half adder and 1 OR gate. Either we can use 1 full adder or 2 half adder and 1 OR gate. Can I use this? Yes, sir. Either you can use full adder, full adder, full adder and full adder. It means if we have to perform addition of n bit, 2 n bit numbers, we can use n minus 1 full adder and 1 half adder. N minus 1 full adder and 1 half adder. So n bit parallel adder can be implemented by n bit parallel adder, n bit parallel adder can be implemented by first we have n number of full adders that we have already observed, this n number of full adders. Yes sir, we can also use n minus 1 full adder and 1 half adder. We can use n minus 1 full adder and 1 half adder, n minus 1 full adders and 1 half adder. Is it okay? Yes sir. Now we all know one full adder can be implemented by 2 half adder and 1 OR gate. So one full adder can be implemented by 2 half adder and 1 OR gate. One full adder can be implemented by 2 half adder and 1 OR gate. One full adder can be implemented by 2 half adder and 1 OR gate. It means how many half adders are required to implement a n bit full adder? Sir, we required 2, 2, 2, 2. So you can just write 2n minus 1. Is it okay? So 2n minus 1 half adder and n minus 1 OR gate. Can I write like this? Yes, sir. We can implement by using, very important, this asked in many times. So always remember 2n minus 1 half adder, 2n minus 1 half adders and n minus 1 OR gates. How many of you able to understand, Bitaji? 2n minus 1 half adder and n minus 1 OR gate can also implement n bit full adder. How many of you able to understand? Please let me know by writing in the comment section, Bitaji. How many of you able to understand? Please let me know by writing in the comment section. Great. So now we know about the full adders as well. Let's have one more part. Please observe its advantage and disadvantage. So there is only one advantage. Even if you have given the job to design a group adder, you will design the parallel adder only. Is it okay? Yes, sir. Because that is what we are doing. So you will design the same. So it's very simple and easy to design. Very simple and easy to design. Is it okay? Now, please observe the disadvantage part. So up to this part, everything is clear. Hello, hello. Yeah, great. Now, please observe what is the disadvantage. For a n bit parallel adder, if each logic gate delay, this is a condition, because we all know that logic gates will have different delay. Especially a XOR gate and basic gate will have different delay. XOR gate delay is more than the basic gate delay. Okay, but theoretically, if we talk, if we have n bit parallel adder and if each logic gate will have a delay of TPD, then minimum time delay required for addition of two n bit number in a parallel adder is equals to 2 into n TPD. We have observed for 4 bit we required 8 TPD time. Is it okay? Yes, sir. And that makes the adder very slow. So hence parallel adder is very slow comparative to carry look ahead adder, we can say. And also the addition time varies with the input, number of input as well as input data. So addition time varies with input data. Time varies with number of bits and input data. So time varies with number of bits and input data. Is it okay, Bitaji? Please let me know by writing in the comment section. Great. Let's try to have some questions based on the parallel adder or a ripple carry adder. Please observe the first one. Suppose if we have 1 bit full adder, and this 1 bit full adder, I'm just changing the data a little bit. Otherwise, it will be easier for you to answer. Suppose we have 1 bit full adder, and 1 bit full adder takes 10 nanoseconds. 1 bit full adder takes 10 nanoseconds to generate carry out bit and 20 nanoseconds to generate sum out bit. 20 nanoseconds to generate sum out bit. Then calculate the maximum rate of addition per second when 4 single bit full adders are cascaded. When 4 single bit full adders are cascaded. Can you answer this one, beta ji? Can you answer this one? We have a 1 bit full adder which takes 10 nanoseconds to generate carry out bit and 20 nanoseconds to generate sum out bit. So here the XOR gate and XOR gate and basic gates will have different delay. Okay. Previous data is of engineering services question asked in 2005. I have just changed the data. Okay. So please observe here. Can you answer now? See, beta ji, please observe. Everyone, please observe. Sir, we have total 4 single bit full adders. So 4 1 bit full adders means 1, 2, 3 and 4. We have 4 1 bit full adder. Yes, sir. Full adder will have, sir, A0, B0 and we have C0. Okay. Again we have A0, A1, B1 and A2, B2 and A3, B3. The data is not given. Only given that how much time it would take to generate carry and how much time it would take to generate sum bit. Okay. So we have 1 full adder, 1 bit full adder. We have 1 bit full adder, we have 1 bit full adder, we have 1 bit full adder, we have 1 bit full adder. And the output carry of least bit will become input of next, and it goes so on. Can you please try to answer what is the rate of addition, beta ji? S1, C, S1, C2, S2, C3, S3, C4. Now please observe once again. I just tried to show you here once again how much time it would take to generate carry bit. Sir, it takes 10 nanoseconds to generate carry bit. It means AND gate and OR gate operation of a full adder will perform in just 10 seconds. However, A XOR B XOR C operation performs in 20 nanoseconds. Yes, sir. So it would take 10 nanoseconds to generate carry bit and 20 nanoseconds to generate sum bit. We have A0, B0. We have A1, B1, we have A2, B2, we have A3, B3. But the addition of A1, B1 will be valid only when C1 is present. With the initial carry, we can assume 0 because initial carry is not given. Is it okay? Yes, sir. Now please observe here. So A0, B0, whatever will be A0, B0, it would take 20 nanoseconds to generate some bit and take 10 nanoseconds to generate carry out bit. So after 10 nanosecond, irrespective of whether S0 is generated or not, after 10 nanosecond, the input C1 is available. Is it okay? So now the data onto the full adder 1 is valid after 10 nanosecond. After 10 nanosecond, now it would take 20 nanoseconds to generate some bit. So after 10 nanosecond, this will start addition and it would take 20 nanosecond for sum. So total from initial it will become 30 nanosecond. After 10 nanosecond, data is present here. With the valid data, carry will be get generated 10 plus 10, 20 nanosecond. So from initial, after 20 nanosecond, we have C2. Is it okay? irrespective whether S0 is present or not, S1 is present or not, we have C2. If we have C2, it means the valid data on full adder 2 is available. Now it would take 10 nanosecond. It would take 10 nanosecond to generate carry bit and 20 nanoseconds to generate sum bit. After 20 nanosecond, we have a valid data. Then 20 nanosecond will become 40 nanosecond. It means S2 valid is available after 40 nanosecond. However, C3 valid is available after 30 nanoseconds because 20 plus 10. Is it okay? After 30 nanosecond, all the three valid inputs are available to the input of full adder 3. It would again take 10 nanoseconds to generate carry bit and 20 nanoseconds to generate sum out bit. So this will be generated in 40 nanosecond, but the S3 will be available 30 plus 20, 50 nanosecond. It means what? This means one addition is performed if all the sum bit and carry bits are available. What is the minimum time delay required for this adder to perform an addition? Sir, one addition will be performed in 50 nanosecond. How many of you are able to understand? Yes, sir. Can I generalize in a formula way? Please observe, beta ji. Please observe, beta ji. This is the worst case delay. Okay, so time for one addition in parallel adder, in n-bit parallel adder, in n-bit parallel adder is equals to, please observe beta ji, we have to wait till C3 get generated. And how much time the C3 will take? Sir, n minus 1 into C out time. It means, please observe here, since we have 4 bit, so 4 bit, so 4 minus 1, 3, 3 into 10 nanosecond is the carry out time for C3. Means C3 is available. Is it okay? Now, whether C4 or S3, whichever will take more time, that is the time we need to add such that we have total time period available required by a full adder to perform one addition. So please observe here. Can I write S out or C out? Whichever is maximum. Whichever time is maximum. S out time or C out time, whichever is maximum. S out time or C out time, whichever is maximum. How many of you able to understand, beta ji? Please let me know by writing in the comment section. Can you please let me know by writing in the comment section, beta ji? Great, sir. So we have a generalized formula for the worst case delay. However, if the data is given, this formula is not valid. This formula is valid if the data is not given. Is it okay? Or worst case delay we are talking about. Is it okay? When we don't know about the input data, we can use this formula to calculate the time period required for one addition. Is it okay? So you can say, sir, in this we have 4 bit, 4 minus 1 into carry out time 10 nanosecond plus whichever is maximum. So 20 nanosecond is more. So we have this as 50 nanosecond. One can say, sir, in 50 nanoseconds, in 50 nanoseconds, one addition is performed. Is it okay? Yes, sir. So if we talk about 1 second, because we have to calculate rate of addition, it means number of additions per second. So this will become 1 upon 50 nanosecond 10 to the power of minus 9. This is addition. So what is the rate of addition? One can say, sir, rate of addition in addition per second. Rate of addition in addition per second will become 10 to the power of 9 by 50. So 10 to the power of 9 by 50. You can say, sir, this will be equals to 2 into 10 to the power of 7 additions per second. So this is the rate of addition. Still you are saying that it is a slower. Yes. What is the rate of addition? It can perform 2 into 10 to the power of 7 additions per second. It can perform 2 into 10 to the power of 7 additions per second. Still it is slow. Still it is slow. How many of you able to understand this question perfectly? How many of you able to understand this question perfectly? Please let me know by writing in the comment section. Can you solve one gate question as well? Let me show you what kind of question. This is a gate PYQ. I just wanted to show you how to utilize our information to solve such questions. Okay. So can you answer this one? Can you answer this one? Can you answer this one, beta ji? Can you answer this one? A 16-bit ripple carry adder, a 16-bit ripple carry adder is realized by using 16 identical full adders as shown in figure. The carry propagation delay of each full adder is 12 nanosecond. It means in order to generate carry, it would take 12 nanoseconds, and the sum propagation delay for every full adder is 15 nanosecond. The worst case delay of this 16-bit full adder is dash nanosecond. So all of you are now know about the basic formula approach. So can we use the basic formula approach? Yes, because it's a worst case delay and data is not given. Whenever data is not given, it will become very easy. Whenever data is not given, it will become very easy. The only challenging when the data is given. In case if the data is not given, it is very easy. How to go, sir? We need to find how much time worst case delay for 16-bit adder will be. How much time it would take for one addition. So how much time it would take for one addition? Time for one addition. Worst case delay or time for one addition. This is the minimum time for one addition. Basically, this is a minimum time for one addition in worst case. Minimum time for one addition in worst case. Is it okay? Yes, sir. We are talking about worst case delay. Worst case. Okay. So addition, for one addition, worst case delay will be. So sir, we have n-1 C out time. So it's a 16-bit. 16-bit means 15 minus 1. C out time. What is C out time? It is 12. And plus of 12 or 15, which is more? 12, 15 is more. So 15. So how much time this is? 13 into 12, 15 minus 1, na? 14 into 12 plus 15. How much time it would take? Please let me know by writing in the comment section, beta ji. Haan ji. We have 16, na? Sorry, beta. We have 16, na? We have 16. 16-bit full adder. So n minus 1 into 12 plus 15. So this will become 15 into 12 plus 15, or you can just write 15 into 13. Okay. So you can even write it like 15 into 13. Because if we take 15 common, then 15 into 13. So 15 into 13 means 195. It would take 195 nanoseconds. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. How many of you able to understand this case? This is the worst case we have, because here we have a full adder. Suppose if instead of full adder they have indicated a half adder, then if they have indicated a half adder, then sir, then for this particular one, in case if the carry out time and sum out time is coming from the different delays and they have given the half adder delay as well, that we have to consider first. Is it okay? So what we will do, we will go with the instead of going with the n minus, we have to observe here how much time it would take. Is it okay? And then we have to do the multiplication. How many of you able to understand, beta ji? Please let me know by writing in the comment section. Great. Let me make the question little bit more difficult. I'm just giving this question as a homework to all of you, because the same kind of question already we did. Now let's talk about this one. Okay. This is very important one and different from what you have learned so far, because here we have a data. Whenever data is given, then the approach to find out minimum time delay after which your output will get stable, or output a correct output is available, that changes. So please observe one question. This is very important one, very important question. Please observe. Figure 1 shows a 4-bit ripple carry adder. Figure 1 shows 4-bit ripple carry adder. 4-bit ripple carry adder. So we have figure 1. Figure 1 shows 4-bit ripple carry adder. This one. Figure 1 shows 4-bit ripple carry adder. Okay. By using full adder, and we have given the form of xy. So x3, y3, x2, y2, x1, y1, x0, y0. And figure 2 shows the circuit of full adder. Circuit of full adder is, this full adder is implemented by 2 half adders and 1 OR gate. This full adder is implemented by 2 half adder and 1 OR gate. Okay. So this is the circuit. Circuit is we have x, y and x, y and z. So here it is in the form of z or c. Let me write z. So z0, z1, z2, z3 and z4. It is in the form of z. Okay. We have a sum bit and a carry bit. We have a sum bit and the carry bit. This is the circuit which we are using. Is it okay? Yes, sir. So in figure 1 shows a 4-bit ripple carry adder realized by using full adder. We realized by using full adder, and the circuit of full adder is shown in figure 2. Is it okay? So we have one figure 1, and we have figure 2. Now next is the propagation delay of XOR gate, AND gate. Please observe, beta ji, very good question. The propagation delay of XOR gate, AND gate, OR gate in figure 2 are 20 nanosecond, 15 nanosecond and 10 nanosecond respectively. So in this we have a delay of 20, 15 and 10 nanosecond respectively. Assume all the inputs of a 4-bit adder is initially resetted to 0. Very important information. Assume all the inputs of a 4-bit full adder initially resetted to 0 at time t is equals to 0. The input to 4-bit is changed. X3, X2, X1, X0, 1, 0, 0, Y3, Y1, Y2, Y0, 0, 1, 0, 0, Z0, 0. The output of the ripple carry adder will be stable in t nanosecond is, where t is. Is it okay? So you have to identify the output of a full adder will be stable in say dash nanoseconds. You have to identify this dash nanoseconds. How many of you able to understand this question? Can you identify the worst case delay? Yes, sir, we can identify the worst case delay. It is very easy. How can you identify the worst case delay? Sir, basically XOR gate will have a delay of 20 nanosecond. So 20 nanosecond, that indicates some bit will come in 40 nanoseconds. Is it okay? And if we talk about carry bit, then carry bit will take, this will come 20 nanosecond. This will come after 20 nanosecond, and this would take this would come after 20 nanoseconds, and this would take, sir, it will be available 20 plus AND gate is of 15 nanoseconds, and then OR gate is of 10 nanoseconds. So 20 plus 25. Okay. So one can say, sir, in 40 nanoseconds we have a sum bit, and in 45 nanoseconds we have a carry bit. If the data is not given, we know that carry bit is after 45 nanosecond. So you can just go write down like that. N minus 1, that is 4 minus 1 into C out time 45 nanosecond plus 45 nanosecond. That is the worst case delay in case if the data is not given. But here the data is given. Initially we have 0, 0, 0, and then at t is equals to 0, the data changes to 1, 1, 0, 0 for x and 0, 1, 0, 0 for y. How many of you able to understand, beta ji? Are you able to understand the question? Can I start doing the solution part? Very good question and very important as well, because in this entire topic, this is the one that can be asked. Rest everything is very easy. You can easily answer as well. Now please observe how to solve this question. Let's have a discussion to this question. How to solve this question? What is the initial data? Means before t is equals to 0. So before t is equals to 0, I am considering t is equals to 0 minus. T is equals to 0 minus means before t is equals to 0. Before t is equals to 0. So before t is equals to 0, if we talk, before t is equals to 0, if we talk, means t 0 minus. We have x3, x2, x1, x0 as 0, 0, 0, 0, and y3, y2, y1, y0 as 0, 0, 0, 0. So what is the result we have? We have the result as 0, 0, 0, 0, and C4 is also, Z1 is also 0. Is it okay? Yes, sir. So up to this, the data is this, before t is equals to 0. Is it okay? At t is equals to 0, the data is changed. At t is equals to 0, the data is changed. Now, at t is equals to 0. At t is equals to 0. If we talk about at t is equals to 0, what is the data of x3, x2, x1, x0? It changes to 1, 1, 0, 0. And what is the data of y3, y2, y1, y0? The data of y3, y1, y3, y2, y1, y0 will become 0, 1, 0, 0. The data is changed. How many of you can see this? Great, sir. Is it okay? Great, sir. So if you talk about before t is equals to 0, from minus infinite time to t is equals to 0, from minus infinite time to t is equals to 0, the circuit is in this state. So in this state, what is the carry available here? What is the carry available here? That is 0. What is the carry available here? That is also 0. What is the carry available here? That is also 0. What is the carry available here? That is also 0 initially. And at t is equals to 0, if you observe, the data changed, but there is no change in x0 and y0 value. So if there is no change in x0 and y0 value, it means S0 will remain same as it is before. Yes, sir. And Z1 will remain as it is before. Is it okay? Yes, sir. If we add these three, then also we get S1 as a 0 as well as Z2 as 0. So there is no change in data till Z2. after t is equals to 0, we can see there is no change in data till z2. Is it okay? Yes, sir. Now, when we perform the addition of z2, x2 and y2, 0, 1, 1, what we will get? Now, when we perform the addition of z2, x2, y2, what we will get? 0, 1, 1. 0, 1, 1. We get S2 to be 0 and we have Z3. Now, what is Z3, beta ji? Z3 will become, we have a Z3 will become logic level 1. So, Z3 changed. Z3 changed. Is it okay? And now, when these three get added, we have Z4 and S3. So, 1, 1, 0. 1, 1, 0 means, 1, 1, 0 means we get 0 carry over 1. So, Z4 and S3 are needed. How many of you able to understand? Yes, sir. So, till Z2, before t is equals to 0 and after t is equals to 0, data till Z2 will remain same. Data till Z2 will remain same. Yes, sir. So, it means the addition of this up to this part will remain same. There is no change. Z0, Z1 and Z2. Till Z2, we have same data. Till Z2, we have same data. How many of you able to understand? Till Z2, we have same data. Yes, sir. Now, when Z2 is the same, we will talk about S2. Till S2, there is no change in the data. Till S2, there is no change in the data. We will talk about S3 and Z3. So, let us first discuss about for Z3. For Z3. If we talk about for Z3, then actually we have used 2 XOR gate and 1 OR gate. 2 XOR gate, 2 half adder and 1 OR gate. 2 half adder and 1 OR gate. Is it okay? Yes, sir. Now, please observe, Bitaji, I need your full concentration because this is very important part as well. Yes. This is your C3, Z3 and we have this data. Okay. Yes, sir. Now, please observe everyone. I need your full concentration, Bitaji, to understand this particular thing. Okay. We all know about the different logic gate delays. Yes, sir. XOR gates will have a delay of 20 nanosecond. AND gate will have a delay of 10 nanosecond. XOR gate will have a delay of 20 nanosecond. AND gate will have a delay of 15 nanosecond. And OR gate will have a delay of 10 nanosecond. Is it okay? Yes, sir. Now, please observe here, Bitaji. So, what is the data we have applied here? Till Z2, there is no change. Z2 is 0. There is no change till Z2. However, X2 and Y2 data will now become 1, 1. Is it okay? Till this part, there is no change. Only at this part, there is a change. So, the part where no change, we need not to wait for Z2 to come. That is already 0. We have already Z2 0. Is it okay? So, we need not to have this 0 to come, this 0 to come. It is already up to this part, everything is as before. Is it okay? But now if you observe 1, 1, what is 1, 1? For same we get 0. Is it okay? Yes, sir. And for same 1, 1 we get 1. Is it okay? Yes, sir. We are getting 1 here. So how much time this? We have input X2 and Y2 which is initially available. All the data initially available. X2, Y2, X1, Y1, X3, X2, X1, X0, Y2, Y1, Y3, Y0. That is already we have. So how much time it would take? It would take 15 nanoseconds to generate this. And once we have this, if one input of OR gate is logic 1, irrespective of other input, if one input of OR gate is logic 1, irrespective of other input, irrespective of the data on other input, what is the output, beta ji? What is the output, beta ji? We all know if one input of OR gate is logic 1, irrespective of the data on other input, output is logic 1 only. So we are getting Z3 to be 1 in how many seconds? After how many seconds from initial we are getting Z3 high? 15 plus 10. How many seconds we have to wait? 25 nanoseconds. So that is Z3 is equals to 1. We get after 25 nanoseconds after 25 nanoseconds. How many of you able to understand? So now we have Z3 and X3 and Y3 is already available to us. X3 and Y3 is already available to us. Again observe. We have two half adder and one OR gate. We have two half adder and one OR gate. Now I am interested in S3 and C4, because when S3 and C4 is available, we can say the data is available. So Z3 we are getting after 25 nanoseconds. Z3 we are getting after 25 nanoseconds. Z3 we are getting after 25 nanoseconds from initial. So Z3 is available 1 after 25 nanosecond from initial. Is it okay? And what about X3 and Y3? X3 and Y3 is already available at t is equals to 0 only. Is it okay? Yes, sir. Now, please help me to identify time required for the T4 and S3. So, 25 nanosecond, and this is logic level 1. Is it okay? Since both X3 is 1 and Y3 is 0. X3 is 1 and Y3 is 0. So, this data is also important for us. Is it okay? Yes, sir. And what we will get it? 1, 0. What we will get it? 1, 0. For different, we get 1. And how much time it would take? How much time it would take? Sir, this will be available from initial time. This will be available from initial time after 20 nanosecond. That 20 nanosecond is the delay of this XOR gate. However, the other input Z3 is available after 25 nanosecond. Always remember, the logic gate output will be considered only when both the inputs are available. You can understand like we have a train and the signal goes, or you can say the train moved ahead only when all the passengers will reach. So this passenger is reached after 20 nanosecond, but we don't get output. We don't get correct output until unless we have this passenger output comes as well. So this is coming after 25 nanosecond. So let all of them get boarded to the input first. Is it okay? Yes, sir. So now we have 25 nanoseconds. So 25 nanoseconds, and then this will take another 20 nanoseconds to perform its operation. And what we will get, sir? This is logic level 1, 1, 1, we will get 0. S3 we are getting 0. And S3 initially also we have 0 only. So how much time it would take, sir? It would take 25 plus 20, that is 45 nanoseconds. So 45 nanoseconds are needed to have S3 output. 45 nanoseconds we have to wait for S3 to come. Is it okay? Yes, sir. And if you observe this 1, so we have this logic level 1 here. That is 25 nanosecond. Post 25 nanoseconds we have this logic level 1. And this we have available post 20 nanosecond. So out of these two, this will be available post 25 nanoseconds. Is it okay? Yes, sir. And 1, 0, so this will give 0, this will give 0. So it means OR gate, this input will don't have any function. We have to wait for this input to come. After 25 nanoseconds, we have both the inputs as 1, 1 from initial. It would take 15 nanoseconds. So after 15 nanoseconds, we get logic level 1, and after 10 nanoseconds, we have output C4. So how much time it would take? Sir, this will be available in 20, but this will be available in 25. 25 plus 15 plus 10. So how much time it would take for C4 to generate? How much time it would take for C4 to generate? C4 will be generated in 25 for Z3 plus this AND gate operation 15 nanosecond plus this OR gate operation 10 nanosecond. Beta, can you please tell me how much the time is going on? That is 50 nanoseconds. So after 50 nanoseconds, we have both sum and carry. How many of you are able to understand? Please let me know by writing the comment section, beta ji. So the output is stable. Worst case delay is different. For the data given, the output is stable after 50 nanosecond. Whatever the data we are getting after 50 nanosecond, that data is not changed. If we have input data from 000 initially changes to this value. Why? Because up to Z2 already the data is available. Only post Z2, how much time it would take Z3 to have and how much time it would take to S4, S3 and C4 to have, we have to calculate. So whenever data is given, always be cautious and follow the given data information. Is it okay? In case if the data is not given, always go with the conventional method. So here the correct answer is 50 nanosecond. How many of you able to understand, Betaji? So here the correct answer is 50 nanoseconds. How many of you able to understand this question perfectly? Please let me know by writing in the comment section, Betaji. How many of you able to understand this question perfectly? Please let me know by writing in the comment section, Betaji. Any one of you have any doubt? Please feel free to ask. Okay, great. It's my request from all of you. Please go through this question once more during your revision. Is it okay? Great. Now come to the overflow indicator. Please write down. Please write down 4-bit ripple carry adder or parallel adder with overflow indicator. Parallel adder with overflow indicator. Okay. So we have a 4-bit parallel adder with overflow indicator. See, here we have, consider A, A3, A2, A1, A0 and B, B3, B2, B1, B0 are 2's complement are 2's complement signed numbers. Suppose if I make a question like here we have a LED and the LED will display error or it will display the result S3, S2, S1, S0. So we all know that in case if the overflow indicator will become high, then your LED should represent error signal because that indicate it is out of the range. All of you have done in your calculators as well. When you put in a calculator 10 to the power of 1000 multiplied by 10 to the power of 1000 into answer, if you do like this now, what happened? 1 or 2 times it will shows error. Why this error signal will be there? Because you have crossed the limit which calculator can represent. In the same way, if we have this 4-bit and if the overflow occurs, then overflow occurs means we can't represent in 4-bit. Now we need 5-bit to represent that. Under such a condition, you can say the result is not correct. Is it okay? So error signal will be displayed. How many of you able to understand, Betaji? Already I told you, if the carry into last bit position and carry out from last bit position are different, overflow occurred. If they are same, no overflow occurred. Is it okay? Great, sir. Now let's talk about look ahead carry adder. Sir, where is the MCQ available for the topics to practice? First go with the GATE PYQs. Now if you observe, we have a GATE Wallah PYQ book as well. See, I can just represent you this volume 1. This is a ESC. It is not here. Let me see if some book is presented here. Yeah, great. See, this kind of books are available in the market or onto the websites as well. your PW website was also. So here you can see now, like questions are available in topic wise format. So in a topic wise format, like we are currently studying combinational circuits. Okay. So if you observe in a combinational circuit, you will get these kind of gate questions. First, you have to go with the gate question. Is it okay? Now you have three branches. First is your computer science engineering, and electronics and electrical. So it doesn't matter what is your branch. You have to do the common questions of other branch as well. Like if you are this year, if you are going to appear with the electrical or electronics, then you have to solve the question PYQs of digital electronics of CSC, instrumentation, EE and ECE. Is it okay? So that much of questions are sufficient. You will have a sufficient different type of questions to practice. If you want more, then you can go with the engineering services PYQ first, because there is very high chances that same question with the same data is going to be designed in some PSU. Okay. After that, if you got sufficient time, then you can go with some practice books. There are a lot of practice books as well. I can't take the name directly, but there are some authors which are very good. So you can opt them, or you can take the practice book of Wallah. That is also a great question combination will be there. Okay. And you can start your practice. So there is a free sources, that is Gate PYQ. And if you want, you can have a practice books that is available in the market. You can take the Gate Wallah practice book. Okay. That is available with the Infinity batch as well. You can just arrange with some of your friends. Now come back to the part. Okay. See, we have studied so far about parallel adder, ripple carry adder. Okay. So in a ripple carry adder, we have seen we have to wait for a carry to generate. Is it okay? If we can design such a adder in which all the carries can generate it parallelly, then your circuit will become very fast. If all the carries can generate parallelly, the entire addition will be done in just one full adder delay. Is it okay? Yes, sir. So this is possible with a simple design of circuit called carry look ahead circuit. So if we design a carry look ahead circuit or look ahead carry circuit, both are the same thing. In different books they have represented in a different way, then we can do the addition directly. Is it okay? Yes, sir. So let's have a discussion of carry look ahead adder. Carry look ahead adder. Please observe, beta ji. It reduces the propagation delay by complex circuit. This is very important for CSIT. Very important for CSIT. CSIT both are the same only. So ECE and IN. Okay. Previously also some questions are asked, and there is a possibility that they are going to ask in 2027 as well. So it reduces the propagation delay by introducing complex hardware. This is fastest carry adder among all. In this look ahead carry circuit is used. In this look ahead carry circuit is used. Is it okay? To generate carry parallelly. To generate carry parallelly. Is it okay, beta ji? Yes, sir. Let's try to understand. Okay. So all of you are aware with the one full adder by using two half adder and one OR gate circuit. All of you are aware with one full adder by using two half adder and one OR gate circuit. Yes, sir. So suppose we have two half adder AI, BI and two half adder and one OR gate circuit. Okay. So please observe AI, BI, CI is the carry, and we are getting SI as a sum bit and CI plus 1 as a next carry. Please observe, beta ji. Let us suppose the first half adder output of XOR gate is a propagating term. So I'm just writing Pi, and the output of this AND gate say generating term, that is GI. Is it okay? So SI can be represented as Pi XOR Ci, and we have this as Pi dot Ci plus Gi. So Pi Ci plus Gi. Can I write like this? Yes, sir. Where I is the ith, where I is the ith significant bit. Now let's talk about what is ith significant bit. See, we have propagating term Pi. What is propagating term Pi? It can be clearly observed the propagating term Pi is Ai XOR Bi. So Ai XOR Bi. Is it okay? We have a data A0, A1, A2, A3 and B0, B1, B2, B3. So if we talk about a 4-bit, we have a P0. P0 can be represented as A0 XOR B0. In the same way, what is P1? P1 is A1 XOR B1. In the same way, can you write P2 as A2 XOR B2? Yes, sir. Can you write P3 as A3 XOR B3? Yes, sir. In the same way, for generating term, if you observe a generating term GI, what is GI, beta G? GI is AI dot BI, AND gate operation. So it indicates G0 is A0 dot B0, G1 is A1 dot B1, G2 is A2 dot B2, and G3 is A3 dot B3. Is it okay? So for a 4-bit, we have A3, A2, A1, A0, B3, B2, B1, B0. So that I am representing in a 4 different full address. Is it okay? That is what a ith unit for P0, P1, P2, P3, so on. In the same way, can you write for S1? What is SI? SI is Pi XOR Ci. We all can see from the circuit, SI is Pi XOR Ci. It means S0 is P0 XOR C0, S1 is P1 XOR C1, S2 is P2 XOR C2, and S3 is P3 XOR C3. Now, when I observe this, I will be able to understand that in case if the carry bits are available with us, then we can have a sum bit directly from the generating bit and from the generating bit GI and Pi. Is it okay if we have all the carries? How to generate all the carries at the same time? For that, please observe carry, next carry Ci plus 1. What is Ci plus 1? Pi Ci plus Gi. So if I am interested to write carry C1, so carry C1 will become P0 C0 plus of G0. Great. This expression shows us we can write the next carry C1 in terms of propagating term, generating term and initial carry. Great, sir. Can I write C1 plus 1? That is we have C2. So C2, if we talk about C2, what it become? Sir, I is equals to 1. So P1 C1 plus G1. So we can write P1 and C1 can be represented as P0 C0 plus G0. Then we have plus of G1. So that indicate we can generate C2 as well from the propagating term and generating term and initial carry. By the information of P1, P0 C0 plus of P1 G0 plus of G1. If we have the information of initial carry C0 and all the generating and propagating term, we can generate C2 as well. In the same way, can you generate C3? Yes, sir. C2 plus 1, C3 will become P2 C2 plus of G2. So if I replace C2 with what we have get as P1 P0 C0, so this will become P2 P1 P0 C0 plus of P2 P1 G0 plus of P2 G1 plus of G2. So it means with the information of initial carry C0 and all propagating and generating term, we can have C3 at the same time when we have C1, when we have C2, at the same time we have C3 as well. In the same way, we can generate for C4 as well. How many of you able to understand, beta ji? Great, sir. In the same way, we can generate for C4 as well. In the same way, we can generate for C4 as well. How many of you able to understand, beta ji? C3 plus 1, that is C4. We have P3 C3 plus of G3, and we can replace this C3 with this entire content. Is it okay? Yes, sir. So when you are going to write, it will become P3 P2 P1 P0 C0 plus of P3 P2 P1 G0 plus of P3 P2 G1 plus of P3 G2 plus of G3. Is it okay? Great, sir. It goes on, and you can generate the carry just by the information of propagating term and generating term and with the initial carry. So this Ci plus 1 expression suggests us that we can create a complex circuit to reduce the time of operation and to increase the speed of operation of a full adder. Let's have a discussion of a 4-bit carry look ahead circuit. If we talk about 4-bit carry look ahead circuit, then first of all we need generating and propagating term. We need generating and propagating term. To propagate we need XOR gate. To generate we need AND gate. For 4-bit we need 4 XOR and AND gate combination. Is it okay? Yes, sir. We have A0 B0, A1 B1, A2 B2, A3 B3. So A0 B0, A1 B1, A2 B2, A3 B3. This is the data we have available onto the we have the data available which we want to perform the addition. Is it okay? Yes, sir. And if we get carry, then just by the output of XOR gate we have the output 1, 2, 3, 4, S3 and C4. So we can have S0, S1, S2, S3 and C4. Is it okay? Yes, sir. That can be represented as P0 C0. Then we have to generate P1 C1. Then we have to generate P2 C2. Then we have to generate P3 C3. So definitely if we have all the carries, we can have all the sum at the same time. Is it okay? Yes, sir. Now suppose we have an initial carry C0 available here. So we have an initial carry available here. Is it okay? And after a one logic gate delay, if I consider a OR gate and XOR gate and AND gate will have same delay. So after one propagation delay, we have a propagating term P0, G0, P1, G1, P2, G2, P3, G3, all available just after one propagation delay. We have data after one propagation delay, all the outputs, all the propagating term and generating terms are available. Is it okay? Yes, sir. And when we see the carry expression, what is C1? C1 is basically P1 C0, P1 C0, G0, P1 C0, G0. How many of you able to understand? Please let me know by writing in the comment section, beta ji. So we have a C1. In the same way, if you observe, what is your C2? C2 is having 2 AND gate and 1 OR gate. C2 having two AND gate and one OR gate. C2 is we all can see C2 is basically C0, P0, P1, P1, G0, G2. How many of you able to understand, beta ji? You can observe here. In the same way, if we observe C3, so C3 will have three AND gate, 1, 2, 3 and one OR gate. Now, depending upon the fan in, we can keep it two levels only, but with the increase in number of bits, there is a possibility that we have to use the 2 or 3 AND gates to have possible fan ins. Is it okay? Yes, sir. But theoretically, we say any number of inputs are possible. Then we have only two levels. One is an AND gate level, and another one is a OR gate level to have all the carries after having propagating and generating terms. So this is your P3, P2, P1, P0, P2, P2, P1, P0, C0, P2, P1, G0, P2, P1, P2, G1 and G2. In the same way, if we talk about the fourth C4, we need 1, 2, 3, 4 AND gate and one OR gate. How many of you able to understand? Please let me know by writing in the comment section, beta ji. Every time one more input is being increased, every time one more input is being increased. How many of you able to understand up to this part? Please let me know by writing in the comment section. Yes, sir. So this circuit is called as look carry ahead circuit, called LCA circuit. So carry look ahead adder contains look carry ahead circuit, and look carry ahead circuit is a two level AND OR gate circuit. Now if you observe for any number of bit, how many logic gates are required? How many logic gate delays are required to have carry? One logic gate delay, another logic gate delay, another logic gate delay. It means after three logic gate delays, 1, 2, 3, if each logic gate will have a propagation delay of TPD, then after 3 TPD, we have all the carries available, and after 4 TPD, we have all the sum available. Is it okay? But there is a possibility that different logic gates will have different delay, and accordingly, we will follow whatever asked in the question. How many of you able to understand, beta ji? How many of you able to understand the group adders, 2's complement, concept of overflow? Very important. These three things, if you are able to understand, range of the different signed numbers, like unsigned numbers and signed numbers. How many of you able to understand up to this part? Please let me know by writing in the comment section, beta ji. Great. Hoping you have enjoyed this session a lot. Hoping all of you have enjoyed this session a lot. Great. So you can take this note through simply by approaching towards the Telegram group. So we have a Telegram group. Here I am showing you. You can join the Telegram group. This is my Telegram group where I am sharing the notes. You can scan this and join in the Telegram. Okay. Also, connect with these two Telegrams. One is your Gate Wallah official Telegram channel group. Here you will get all the updates related to your exam and upcoming subjects, everything. And if you are from electrical electronics instrumentation, then you can join this Telegram as well. Is it okay? For CS student, you can join this one. Later on, from here only, I will give to the link to all other branches as well. Is it okay? Your respective subject teachers as well. So hoping you are able to understand up to this part, beta ji. There is no issue. Great. So I have shown to you about the Telegram. You can join the Telegram respective just by making the pause. You can join. Hoping all of you have enjoyed this session a lot. Now come back to this. Sir, electrical machine. Hoping you have enjoyed this session a lot. So advantages: propagation delay is reduced, provides faster faster logic for addition. Disadvantage: its cost is more. Its cost is more. Is it okay? And complicated circuit because of the large number of two levels and or inverter circuit. So always remember that look carry ahead circuit contains two level and or circuit. Is it okay? Great, sir. In the next class, I am going to move towards the multiplexer and demultiplexer. And one more very important thing, multiplexers and demultiplexers are very important. I have again taken 20 minutes extra and extremely sorry for this. I know that your class is scheduled for 2 hours only, but still I am taking little bit extra class so that maximum portion I can cover. Hoping you have enjoyed today's session a lot. Thank you everyone. Lots of love. We will meet again in the next class, discuss about the multiplexers and demultiplexers. Lots of love. Thank you everyone. Good night.